Chapter 11. Magnetic Materials. Exercises pages 263 to 264. Exercises Q1.1, page 263. Choose the correct option. Intensity of the magnetic field of the Earth at the point inside a hollow iron box is 1. Less than that outside 2. More than that outside 3. Same as that outside 4. 0. Solution. 0. Explanation. No magnetic lines of force passes through the steel box. Exercises Q1.2, page 263. Choose the correct option. Soft iron is used to make the core of the transformer because of its 1. Low coercivity and low retentivity, 2. Low coercivity and high retentivity, 3. High coercivity and high retentivity, 4. High coercivity and low retentivity. Solution. Low coercivity and low retentivity. Exercises Q1.3, page 263. Choose the correct option. Which of the following statements is correct for diamagnetic materials? 1. Mu r less than 1 2. Chi is negative and low 3. Chi does not depend on temperature 4. All of the above. Solution. All of the above. Exercises Q1.4, page 263. Choose the correct option. A rectangular magnet suspended freely has a period of oscillation equal to t. Now it is broken into two equal halves, each having half of the original length, and one piece is made to oscillate freely. Its period of oscillation is t. The ratio of t is. Solution. When the magnet is broken in two equal parts, the new magnetic dipole moment is. Exercises Q1.5, page 263. Choose the correct option. A magnetizing field of 360 m-1 produces a magnetic flux density B equals 0.6 T in a ferromagnetic material. What is its permeability in TMA-1? Solution. Exercises Q2.1, page 263. Answer in brief. Which property of soft iron makes it useful for preparing electromagnet? Solution. An electromagnet should become magnetic when a current is passed through its coil but should lose its magnetism once the current is switched off. Hence, the ferromagnetic core, usually iron-based, used for an electromagnet should have high permeability and low retentivity, i.e., it should be magnetically soft. Exercises Q2.2, page 263. Answer in brief. What happens to a ferromagnetic material when its temperature increases above Curie temperature? Solution. A ferromagnetic material is composed of small regions called domains. Within each domain, the atomic magnetic moments of nearest neighbor atoms interact strongly through exchange interaction, a quantum mechanical phenomenon, and align themselves parallel to each other even in the absence of an external magnetic field. A domain is, therefore, spontaneously magnetized to saturation. The material retains its domain structure only up to a certain temperature. On heating, the increased thermal agitation works against the spontaneous domain magnetization. Finally, at a certain critical temperature, called the Curie point or Curie temperature, thermal agitation overcomes the exchange forces and keeps the atomic magnetic moments randomly oriented. Thus, above the Curie point, the material becomes paramagnetic. The ferromagnetic to paramagnetic transition is an order-to-disorder transition. When cooled below the Curie point, the material becomes ferromagnetic again. Exercises Q2.3, page 263. Answer in brief. What should be retentivity and coercivity of permanent magnet? Solution. A permanent magnet should have a large zero-field magnetization and should need a very large reverse field to demagnetize. In other words, it should have a very broad hysteresis loop with high retentivity and very high coercivity. Exercises Q2.4, page 263. Answer in brief. Discuss the Curie law for paramagnetic material. Solution. Curie's law. The magnetization of a paramagnetic material is directly proportional to the external magnetic field and inversely proportional to the absolute temperature of the material. If a paramagnetic material at an absolute temperature T is placed in an external magnetic field of induction, the magnitude of its magnetization. Exercises Q2.5, page 263. Answer in brief. Obtain an expression for the orbital magnetic moment of an electron rotating about the nucleus in an atom. Solution. In the Bohr model of a hydrogen atom, the electron of charge, E, performs a uniform circular motion around the positively charged nucleus. Let r, v and t be the orbital radius, speed and period of motion of the electron. Then, exercises Q2.6, page 263. Answer in brief. What does the hysteresis loop represent? Solution. A magnetic hysteresis loop is a closed curve obtained by plotting the magnetic flux density B of a ferromagnetic material against the corresponding magnetizing field H when the material is taken through a complete magnetizing cycle. The area enclosed by the loop represents the hysteresis loss per unit volume in taking the material through the magnetizing cycle. Exercises Q2.7, page 263. Answer in brief. Explain one application of electromagnet. Solution. Electromagnets are used for various purposes on a day-to-day basis. For example, electromagnets are used in the large cranes which are used in waste yards. Electromagnets are also widely used in numerous electromechanical and electronic devices. Some of the common uses are given below. Uses in home appliances. Most of the electric appliances used in the home use electromagnetism as the basic working principle. Some electromagnet uses in the home include the electric fan, electric doorbell, induction cooker, magnetic locks, etc. In an electric fan, the electromagnetic induction keeps the motor rotating on and on, making the blade of the fan to rotate. Also in an electric doorbell, when the button is pressed, due to the electromagnetic forces, the coil gets energized and the bell sounds. Uses in medical field. The uses of electromagnets are also seen in the medical field. MRI scan, which is short for magnetic resonance imaging, is a device that uses electromagnets. The device can scan all the tiny details in the human body with the help of electromagnetism. Uses in memory storage devices and computer hardware. The data in ebook gadgets and phones are stored in the electromagnetic format in the form of bytes and bits. The computer hardware is also having a magnetic tape which works on the principle of electromagnetism. Even in the olden days, electromagnets had a huge role in the data storage of VCP and VCR. Exercises Q3, page 263. When a plate of magnetic material of size 10 cm by 0.5 cm times 0.2 cm length, breadth, and thickness respectively, is located in a magnetizing field of 0.5 times 104 A per meter, then a magnetic moment of 5 am2 is induced in it. Find the magnetic induction in the rod. Solution. Exercises Q4, page 264. A rod of magnetic material of cross-section 0.25 square centimeters is placed in a magnetizing field of intensity 4000 A per meter. The magnetic flux passing through the rod is 25 x 10 to 6 Wb. Find out A. Relative permeability, B. Magnetic susceptibility, and C. Magnetization of the rod. Solution. Exercises Q5, page 264. The work done for rotating a magnet with magnetic dipole moment m through 90 degrees from its magnetic meridian is n times the work done to rotate it through 60 degrees. Find the value of n. Solution. Data. Theta 0 equals 0 degrees, theta 1 equals 90 degrees, theta 2 equals 60 degrees, W1 equals northwest 2. The work done by an external agent to rotate the magnet from theta 0 to theta is W equals mb, cos theta 0 cos theta. Therefore W1 equals mb, cos theta 0 cos theta 1. Equals mb, cos 0 degrees cos 90 degrees. equals MB, 1 to 0, equals MB. Therefore W2 equals MB, cos 0 degrees cos 60 degrees. Exercises Q6 page 264. An electron in an atom is revolving around the nucleus in a circular orbit of radius 5.3 x 10 to 11 m, with a speed of 2 by 106 meters per second. Find the resultant orbital magnetic moment and angular momentum of the electron. E equals 1.6 x 10 to 19 c, me equals 9.1 x 10 to 31 kg. Solution. Exercises Q7 page 264. A paramagnetic gas has 2.0 times 1026 atoms per meter with atomic magnetic dipole moment of 1.5 times 10⁻23 am to each. The gas is at 27 degrees Celsius. A. Find the maximum magnetization intensity of this sample. B. If the gas in this problem is kept in a uniform magnetic field of 3T, is it possible to achieve saturation magnetization? Y. Solution. Since the thermal energy of randomization is about 2 orders of magnitude greater than the magnetic potential energy of orientation, saturation magnetization will not be achieved at 300 K. Exercises Q8 page 264. A magnetic needle placed in uniform magnetic field has magnetic moment of 2x 10 to 2 am2, and a moment of inertia of 7.2 x 10 to 7 kg m2. It performs 10 complete oscillations in 6s. What is the magnitude of the magnetic field? Solution. Exercises Q9 page 264. A short bar magnet is placed in an external magnetic field of 700 Gauss. When its axis makes an angle of 30 degrees with the external magnetic field, it experiences a torque of 0.014 Newton meters. Find the magnetic moment of the magnet, and the work done in moving it from its most stable to the most unstable position. Solution. Data. B equals 700 Gauss equals 0.07 Tesla, theta equals 30 degrees, tau equals 0.014 Newton meters, tau equals MB sin theta. The magnetic moment of the magnet is. The most stable state of the bar magnet is for theta equals 0 degree. It is in the most unstable state when theta equals 180 degree. Thus, the work done in moving the bar magnet from 0 degrees to 180 degrees is W equals MB, cos theta 0 cos theta, equals MB, cos 0 degrees cos 180 degrees, equals MB, 1, equals 2 megabytes equals 2, 0.4, 0.07, equals 0.056 J. Exercises Q10 page 264. A magnetic needle is suspended freely so that it can rotate freely in the magnetic meridian. In order to keep it horizontal position, a weight of 0.2 grams is kept on one end of the needle. If the pole strength of the needle is 20 am, find the value of the vertical component of the Earth's magnetic field. Solution. Data. M equals 0.2 grams equals 2x 10 to 4 kg, qm equals 20 am, g equals 9.8 meters s2. Without the added weight at one end, the needle will dip in the direction of the resultant magnetic field inclined with the horizontal. The torque due to the added weight about the vertical axis through the center balances the torque of the couple due to the vertical component of the Earth's magnetic field. Exercises Q11 page 264. The susceptibility of a paramagnetic material is chi at 27 degrees Celsius. At what temperature its susceptibility be chi 3? Solution.